Welcome, curious minds, to another deep dive. Today we're digging into one of organic chemistry's most powerful tools, proton nuclear magnetic resonance. 1H NMR.
That's right.
If you've ever felt a bit lost looking at complex structures or just wished for a better way to grasp the details, well, you're in the right place. Our guide today is Chapter 13 of Clayden, Greaves, and Warren's Organic Chemistry, second edition. And our mission, it's really to go beyond just spotting functional groups.
Yeah, it's much more than that.
We want to show you how 1H NMR reveals these deeper insights mechanism, how functional groups change, even stereochemistry. It's a real window into the molecule.
Absolutely. And, many of you probably remember NMR popping up way back in Chapter 3.
Right, with mass spec and IR.
Exactly. We sort of held back on the full power of 1H NMR then because, let's be honest, it looks a bit more complicated than 13C NMR at first glance.
Definitely seems that way initially.
But the authors, they're not kidding when they call it the chemist's primary weapon in the battle to solve structures.
Yeah.
It might seem tricky, but mastering it? Totally worth it. It's fundamental to understanding not just what a molecule is, but crucially, how it behaves.
Okay, so let's unpack this. Why exactly is 1H NMR seen as so much more powerful than 13C NMR? What's the secret sauce?
Well, it really boiled down to a few key differences. First off, natural abundance.
Ah,
Hydrogen's main isotope, 1H, it's basically 99.985% abundant. Almost every hydrogen atom is NMR active. Now, compare that to 13C,
which is only about 1%, right?
just over 1%, yeah, a tiny fraction. So right away, 1H NMR is inherently way more sensitive. You get a strong signal from pretty much every proton.
So you're not just seeing what's there, but you get a much stronger signal from it. That's a huge advantage.
It is. And that directly leads to the second big point. 1H NMR is quantitative.
Quantitative.
Meaning the area under each peak in the spectrum, the integration is directly proportional to the number of hydrogen nuclei causing that signal.
Ah, the little step curves you see on spectra.
Exactly. Those tell you the ratio of hydrogens in different environments. If you know the total number of hydrogens, you can figure out exactly how many are in each spot. You just don't get that direct count from 13C NMR, where peak heights aren't simply related to the number of carbons.
Okay, that's super powerful for figuring out structures. And then there's something else, something about protons interacting.
Yes, the magnetic interaction, or coupling, this is huge. Protons essentially feel the magnetic fields of nearby protons through the chemical bonds.
They talk to each other.
That's a great way to put it. They talk through the bonds, and this splits their signals into patterns, doublets, triplets, quartets. This reveals the connectivity, how the atoms are linked together.
Which you don't really see in 13C NMR.
Not typically, no. Because 13C is so rare, the chance of two 13C atoms being neighbors is really small, so you usually don't see 13C coupling. And finally, the chemical shifts in 1H NMR, the positions of the peaks, often give a more reliable, nuanced picture of the local chemical environment. So these four things together, abundance, quantitation, coupling, and shift reliability, make 1H NMR incredibly informative.
The basic principle is still the same, though, right? Radio waves, nuclei flipping in a magnetic field.
Fundamentally, yes. It's the same physics as 13C NMR. We're exciting nuclei in a magnetic field with radio waves and detecting the energy released when they relax.
But the scale is so much smaller for protons, like 10 ppm versus 200 ppm for carbon. Why the big difference?
Good question. It's because the electron cloud around a hydrogen nucleus is just simpler. Less variable than around a carbon. Carbon can bond in so many ways, single, double, triple bonds attached to all sorts of atoms, leading to a huge range of electron densities and shielding effects. Hydrogen, it's smaller, usually just has that one bond. So the electronic environment doesn't vary nearly as much. Less variation means a narrower range of shielding, hence the smaller, roughly 0-10 ppm chemical shift scale.
And that integration, the quantitative part, must be amazing for checking formulas. Can you give us a quick example?
Sure, think about something simple like acetic acid, CH3O2H.
Okay.
You run the 1H NMR, you'll see two signals, one for that acidic OH proton and one for the 3-methyl protons.
Yeah.
The integration will show you a clear 1:3 ratio. If you know you've got 4 hydrogens total from, say, mass spec, that NMR confirms 1 acidic H and 3 equivalent methyl H's instantly. It's incredibly useful.
Makes sense.
And just a practical point, we always use deuterated solvents like CdCl3 or D2O.
To avoid seeing the solvent protons.
Exactly. Otherwise, you just see a massive peak from the solvent swamping everything else. That small peak, you often see around 7.25 ppm in CdCl3. That's just a tiny trace of non-deuterated chloroform CHCl3 left over. Usually, you just ignore it.
Right, so we know how many hydrogens there are in each environment from integration. Now, the chemical shift, the peak's position, tells us what kind of environment that is.
Precisely. The chemical shift is packed with information. For protons on saturated carbons, the shift is heavily influenced by electronegativity nearby.
Like how electron pulling the neighbors are.
Exactly. Look at a methyl group. Attach it to lithium, CH3 Li, which is electropositive. The shift is actually negative, like -1.94 ppm. It's super shielded.
Wow, negative.
Yeah. Now, go to the other extreme. Attach it to fluorine, CH3F. Fluorine is highly electronegative. It pulls electron density away, de-shielding the protons, and the shift jumps way downfield to 4.27 ppm.
Huge difference.
It is. And these effects tend to be additive. Add 1 chlorine, CH3Cl, you're at 3.06 ppm. 2 chlorines, CH2Cl2, 5.30 ppm. 3 chlorines, CHCl3, 7.27 ppm. Each chlorine adds more de-shielding.
So you can almost predict shifts based on nearby groups. Are there some, general rules of thumb for common groups like methyls?
Definitely. They're really helpful starting points. For a typical methyl group not attached to anything strongly electron withdrawing, think around 1 ppm.
Okay.
Attach it to something that withdraws electrons a bit, or conjugates like a carbonyl, an amine, a sulfide, an alkene. You're looking around 2 ppm.
Makes sense.
And if it's attached to something very electron withdrawing, especially oxygen, like in ethers, esters, or nitro groups, amides, sulfones, then you're pushing toward 3 ppm or even higher.
And these numbers aren't just labels, they tell you about the chemistry, right?
Absolutely. They reveal the molecule's personality, as you said. Take that nitro group example. It shifts a neighboring methyl way down to about 3.43 ppm. Compare that to a carbonyl group's effect.
Which was around 2 ppm?
Roughly, yeah. So the nitro group has more than double the electron withdrawing punch, spectroscopically speaking.
Yeah.
This isn't just a number. It tells you that nitro group is going to significantly increase acidity nearby, stabilize anions. You're seeing reactivity trends in the NMR shift.
That's really cool. And methyl groups can tell us more than just about electron withdrawal, right? Something about structure and rotation.
Oh, definitely. Think about a T-butyl group, CH33C. All 9 protons show up as one sharp signal, singlet.
Because they're all equivalent.
Exactly. Because of fast rotation around those CC single bonds on the NMR timescale, they all average out to the same environment.
Yeah.
But put 2 methyl groups on a CEC double bond, rotation is locked.
Right.
So now those 2 methyl groups might be different. One could be cis to another group, one trans. You'll likely see 2 distinct methyl signals. It tells you about the molecule's rigidity.
Like with amides too, DMF.
Perfect example. Dimethylformamide, DMF. You see 2 separate signals for the 2 N-methyl groups. Why? Because the NC bond in amides has partial double bond character due to resonance.
Ah, restricted rotation.
Exactly. It slows down rotation enough that the 2 methyls become non-equivalent. One is cis to the oxygen, one is trans. Even in complex rigid cage structures like mertanol, where rotation is impossible, different methyl groups, even different CH2 protons, are locked into unique spots and give unique signals.
And the same ideas apply to CH2 groups and CH groups, just shifted a bit further downfield.
Generally, yes. A simple CH2 group in an alkane chain might be around 1.3 ppm, and a simple CH group around 1.7 ppm, typically about 0.4 ppm further downfield than the corresponding CH3.
Okay.
But again, these shifts are incredibly sensitive. Take the CH proton and the amino acid phenylalanine. Its chemical shift actually changes depending on the pH if you run it in D2O.
Really? How much?
Significantly. In basic D2O, where the carboxyl group is COO and the amino group is NH2, the CH is around 3.6 ppm. But in acidic D2O, where you have COH and NH3 plus fire, it shifts downfield to 4.35 ppm.
Wow. So the protonation state changes the electron withdrawal.
Precisely. It's NMR directly showing you the impact of ionization state on the electronic environment. It's a direct window into the molecule's dynamic state in solution. It's not just static structures we're seeing.
That is amazing. So we can estimate shifts, and you mentioned they're often additive. That must be incredibly useful for piecing together complex structures.
It really is, often remarkably so. Say you have a keto ester, and you're trying to assign a CH2 group stuck between the ketone and the ester. You could start with a baseline CH2 shift, maybe 1.3 ppm.
Okay.
Then add an increment for being next to a ketone carbonyl, maybe plus 1.0 ppm. And add another for the ester carbonyl, maybe another plus 1.0 ppm. So you'd estimate around 3.3 ppm.
And you check the spectrum to see if there's a peak around there with the right integration and splitting.
Exactly. It gives you a powerful way to propose and then confirm or refute structural assignments.
Okay, let's shift gears slightly. The alkene and benzene regions. In 13C NMR, these often overlap, but you said protons sort out nicely here. What's the magic behind that?
The magic is the benzene ring current. It's a really neat effect. Those delocalized pi electrons in benzene. When you put the molecule in the magnetic field, they circulate, creating their own tiny induced magnetic field.
Okay.
And crucially, outside the ring, where the aromatic protons sit, this induced field adds to the main applied magnetic field. So the protons feel a stronger effective field.
Which means they're deshielded.
Strongly deshielded. That's why benzene protons themselves are way downfield at 7.27 ppm. Typical alkene protons are usually more like 5-6 ppm. This ring current effect really separates aromatic protons.
And you can see even weirder effects.
Oh yeah. In molecules called cyclophanes, where part of an alkyl chain is forced over or inside the aromatic ring, those internal protons can be massively shielded by the ring current. You can see CH2 signals way upfield, even at negative ppm values, like negative 0.6 ppm.
Negative ppm, that's crazy.
It vividly shows how powerful these local magnetic fields generated by electrons can be.
And the electrons within the ring itself, substituents, can also tweak these aromatic shifts.
Absolutely.
Yeah.
Take an aromatic amine, like aniline. The nitrogen's lone pair can donate into the ring through resonance.
Right, activating the ring.
Exactly.
Yeah.
It pumps electron density into the ring, especially at the ortho and para positions. This shields those ring protons, pushing them upfield, maybe into the 6-7 ppm range. But interestingly, the nitrogen atom itself becomes more positive because it donated its electrons, so any N-methyl groups might actually shift downfield.
So donation into the ring shields the ring protons, but de-shields the donor group's protons.
Often, yes. It depends on the balance. Simple alkyl groups, though, they don't perturb the ring much. Electron-withdrawing groups, like nitro or carbonyls, do the opposite. They pull density out of the ring, de-shielding the ring protons and shifting them downfield.
And this helps understand substitution patterns.
Immensely. Looking at 1,4,4 dissubstituted benzenes is a classic case. Groups that withdraw by conjugation nitro, carbonyl, nitrile, cause the biggest downfield shifts. Groups that withdraw inductively, like CF3, have a smaller effect. And lone pair donors, like oxygen or nitrogen, can actually be net donors overall, even though they're electronegatives, leading to upfield shifts.
And does this apply to alkenes too? Electron-rich versus electron-deficient ones?
Very much so. Just like with aromatic rings, electron-donating groups, like oxygen in an enol ether, push alkene proton signals upfield, making the double bond electron-rich. Electron-withdrawing groups, like a ketone in a neon or especially a nitro group, pull density away, shifting alkene protons downfield, indicating an electron-deficient double bond.
So you could see a nitrile alkene proton maybe around 7.3 ppm.
Yeah, highly deshielded.
While an enamine proton might be way up at 4.4 ppm.
Exactly. And those shift differences are screaming information about reactivity. You know, the electron-deficient alkene is susceptible to nucleophilic attack, while the electron-rich one might react with electrophiles. It's all there in the shift.
Fantastic. Okay, what about that very distinct aldehyde region, around 9-10 ppm?
Ah, yes.
Yeah.
The aldehyde proton, it's pretty unmistakable. Being directly attached to that electron-hungry carbonyl carbon means it's extremely deshielded.
Makes sense.
So you reliably find aldehyde protons in that 9-10 ppm window. Very diagnostic. You might occasionally see other highly deshielded protons there, like, say, the proton next to nitrogen in some electron-deficient heterocycles, like pyridine, but aldehydes are the main occupants of that region.
Okay. And then the last group, protons directly on heteroatoms like O, N, or S, you mentioned they're a bit less reliable.
They are. Protons like OH, NH, SH have much more variable chemical shifts. Why? Two main reasons. Acidity and exchange.
Exchange.
Yes, these protons can rapidly exchange between molecules, especially if there are trace amounts of acid or base or water around. Think about the OH of acetic acid, very acidic, way downfield around 11-12 ppm.
Right.
Compare that to the OH of a simple alcohol, much less acidic, maybe around 2-5 ppm. Phenols, intermediate acidity, maybe 5-8 ppm. The shift roughly correlates with acidity.
But the exchange is the tricky part.
That's what makes them less reliable for pinpointing structure sometimes. This exchange can be so fast, especially if you run the sample in D2O, that the OH or NH proton signal might broaden significantly or even disappear entirely.
Disappear? How?
Because the proton gets swapped out for a deuterium atom from the D2O solvent. H exchanges with D. Since deuterium-2H resonates at a completely different frequency, the proton signal vanishes. Or you might just see a single averaged peak for HOD, partially deuterated water, formed by exchange between your sample's protons and the D2O.
So they can literally vanish from the spectrum.
They can. It's actually a useful trick. Sometimes add a drop of D2O to your sample, rerun the NMR, and see which peaks disappear. Those were your exchangeable OH or NH protons. It highlights a key principle. Proton exchange on heteroatoms is usually very, very fast on the NMR timescale.
Okay, wow. So integration tells us how many, shift tells us roughly where. But here's where it gets really interesting, right? The coupling. This sounds like the real superpower of 1H NMR.
It absolutely is. This is what lets you map out the carbon-hydrogen skeleton. It tells you which protons are neighbors.
How does that work?
Okay, take cytosine, that DNA base. It has two alkene-like protons on the ring that are next to each other. In the NMR, they don't show up as singlets, they show up as two doublets.
Meaning each signal is split into two lines.
Exactly, because each proton feels the magnetic state of its neighbor. The neighbor can be spin up or spin down, slightly changing the local magnetic field, so the proton resonates at two slightly different frequencies. Now, compare that to 2-Fol6-diaminopyrimidine. Its ring protons are too far apart, separated by nitrogens. They don't feel each other, so they just show up as two sharp singlets.
So the splitting tells you about neighbor.
Precisely. Think of it like this. One proton's little magnetic field slightly perturbs the field experienced by its neighbor, splitting the neighbor's signal. Or you can think about energy levels interacting and splitting. Or just visualize a single peak being split into two by one neighbor. It's how protons talk and reveal connectivity.
And the splitting, the distance between the lines in the doublet, that's the coupling constant, J. And it's measured in hertz, not ppm. Why hertz?
Yes, the splitting is J, the coupling constant measured in hertz. Hertz. This is super important. Unlike chemical shifts, ppm, which depend on the strength of the magnet in the NMR machine.
Right, ppm normalizes for field strength.
The coupling constant J is an intrinsic property of the molecule's structure. It reflects the strength of the magnetic interaction through the bonds. A 7 Hz coupling will be 7 Hz whether you measure it on a 60 MHz machine or a 600 MHz machine. It's field independent.
Okay, that's a key distinction. And Pascal's triangle helps predict these splitting patterns.
Pascal's triangle is your best friend for simple coupling. It tells you the multiplicity, the number of peaks in the signal, and the relative intensities. The rule is n equivalent neighbors split a signal into n+1 peaks.
So 0 neighbors.
Gives a singlet, 1 peak, 1 neighbor.
And then 1, so 1 + 1 = 2 peaks. A doublet, ratio 1.1.
Perfect. 2 equivalent neighbors.
Then 2 will go 2 + 1 = 3 peaks. A triplet, ratio 1.2.1.
Exactly. 3 equivalent neighbors.
And 3 + 1 = 4 peaks. A quartet, ratio 1.3.3.1.
You got it. 4 gives a quintet, 1.4.6.4.1, and so on. This immediately lets you recognize common structural units. Like an ethyl group, CH3CH2. The CH2 sees the 3 equivalent CH3 protons.
So N3, it's a quartet.
Right. And the CH3 sees the 2 equivalent CH2 protons.
N2, it's a triplet.
Exactly. That characteristic quartet triplet pattern screams ethyl group. Same for isopropyl. The 6 methyl protons see the 1 CH proton, so they're a doublet. The 1 CH proton sees the 6 equivalent methyl protons, and 6, so it's a septuplet.
Yeah.
One crucial thing. Identical protons do not couple with each other. The 3 protons within a methyl group don't split each other's signals.
Okay, that makes sense. What if a proton is coupled to 2 different neighbors and the coupling constants aren't the same, like in that chrysanthemic acid example from the book?
Ah, great question. That's when you get more complex patterns. If a proton Hu-sub-A-sub is coupled to Hu-sub-sub with coupling J-sub-sub, and also coupled to sub-sub with a different coupling, J-sub-sub, its signal isn't just a simple triplet. It gets split first by J-sub-sub into a doublet, and then each line of that doublet gets split again by J-sub-A-sub.
So you get 4 lines.
You get 4 lines of roughly equal intensity. We call this a double doublet, abbreviated T. You can measure both J values from the spacing between the lines. It tells you specifically about the 2 different neighbors.
Wow. Okay, so coupling is really mapping the connections, and you mentioned it tells us about 3D structure too. How does that work?
Yes, this is incredibly powerful. Coupling is transmitted through the chemical bonds, not directly through space. The efficiency of this through-bond communication depends on the alignment of the bonds.
Okay.
This is why trans protons on a double bond typically have a much larger coupling constant, usually 15 to 18 Hertz, compared to cis protons, which are typically 10 to 12 Hertz.
Why the difference?
Because in the trans arrangement, the CH bonds are aligned in a way that allows for better overlap and interaction through the sigma bond framework of the double bonds. It's like a clearer communication pathway. The cis alignment is less optimal.
So the J value itself tells you about the stereochemistry, cis or trans.
Absolutely. The magnitude of J is often diagnostic for stereochemistry, especially around double bonds and in rigid ring systems. It's often just as useful, if not more so, than the chemical shift for assigning structures and stereochemistry correctly. Looking at complex patterns, like in cyclohexanone, you can use the specific J values to figure out exactly which proton is which and how they're arranged in space.
So what are the key things that affect the size of J? You mentioned bond alignment.
Right, so number one is the number of bonds separating the protons. We mostly talk about vicinal coupling, 3J sub H sub, coupling through 3 bonds, which is usually the strongest. Number two is the dihedral angle between the CH bonds involved, especially important for coupling through single bonds. Carpless relationship, though, maybe that's for a later dive. And yes, bond alignment, like in cis-trans alkenes. And number three is electronegativity. Electronegative atoms attached nearby can actually reduce the size of coupling constants, presumably by withdrawing electron density from the bonds involved in the coupling pathway.
Okay. And are there couplings over more than 3 bonds, like 4J?
Yes, long-range coupling, usually coupling through 4 bonds, 4J sub H sub, is very small, often close to 0, especially if there's free rotation.
Yeah.
But in certain specific arrangements, you can see it. The most common examples are metacoupling in benzene rings.
Between protons 1 and 3?
Exactly. And allylic coupling in alkenes between a proton on the double bond and one on the adjacent saturated carbon. Both of these are typically small, maybe 1-3 hertz. They often happen when the bonds form a sort of zigzag W shape.
Babu coupling.
That's the nickname, yeah. The W pathway allows for better overlap over the 4 bonds. So even if there's no orthocoupling in a benzene ring, you might still see small metacoupling splitting. It's another subtle clue.
Things get complicated quickly. What happens if 2 protons are coupled, but their chemical shifts are really close together? Not identical, but close.
Ah, yes. That leads to what we call second-order effects, or more simply, distorted patterns. If the difference in chemical shift, measured in hertz, between 2 coupled protons becomes similar in size to their coupling constant Kers, the simple splitting rules, like Pascal's triangle, start to break down.
How does it look different?
Instead of seeing 2 perfect 1.1 doublets, for instance, the inner lines of the 2 doublets, the ones closer to the center of the pattern, get taller, and the outer lines get smaller. It creates a characteristic roofing or leaning effect. The peaks sort of point towards each other.
Like the slope of a roof.
Exactly. Seeing that roofing tells you immediately that those 2 protons are coupled and their chemical shifts are close. We often call this an AB spectrum if it's just 2 protons. As K gets even smaller relative to J, the pattern gets even more complex.
Okay. One last type of coupling on the same carbon, geminal coupling.
Right. Geminal coupling 2J sub H sub, coupling between 2 protons on the very same carbon atom.
Does that happen often?
It depends. For protons on sp2 carbons, like in an alkene or carbonyl group, geminal coupling is usually very small, often 0.3 hertz, sometimes negligible. But for protons on a sp3 carbon, a CH2 group, the geminal coupling can be quite large, typically 10-16 hertz, if the 2 protons are chemically different.
How can they be different if they're on the same carbon?
If the molecule is chiral, or if there's restricted rotation or a rigid ring structure nearby, the 2 protons on a CH2 group might find themselves in different environments. We call them diastereotopic. One might be closer to one group, one closer to another.
Like in mertenol again.
Exactly.
Yeah.
Those bridging CH2 protons in mertenol are diastereotopic. They feel different environments, so they have different chemical shifts, and they couple to each other with a significant geminal coupling, around 9 hertz in that case.
And this is key for stereochemistry.
Absolutely crucial. A classic example is a simple vinyl group. Like in ethyl acrylate, you have 3 alkene protons. Let's call them shuba sub, hub sub sub, hut sub sub. They all couple to each other. You'll see a trans coupling, maybe 16 hertz, a cis coupling, maybe 10 hertz, and a geminal coupling between the 2 protons on the terminal CH2, maybe 4 hertz. Measuring these 3 distinct J values allows you to unambiguously assign which proton is which and confirm the stereochemistry. It's incredibly powerful.
Wow. This really has been a deep dive. 1HNMR is just incredibly rich with information. Integration for counts, shifts for environment, and coupling, weaving it all together to map the structure and even stereochemistry. It truly feels like the master key.
It really is. When you put it all together, chemical shift, integration, and the intricate details revealed by coupling constants, 1HNMR provides an unparalleled view into molecular structure. It's definitely the most powerful spectroscopic tool the organic chemist uses on a daily basis for structure determination and understanding reactivity.
So thinking about all this, what does it mean for you listening? How could really mastering these shifts and couplings, understanding what they're telling you about electron density and bond angles and proximity, how might that unlock new ways to think about designing molecules? Especially considering how NMR shows us the dynamic nature of bonds and structures, not just static pictures. Something to ponder. Thank you for joining us for this deep dive and for being part of the Last Minute Lecture family.